तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, I had demonstrated to you that if an amplifier has a gain A and it is having a single pole, the gain of the amplifier DC gain is A naught and its bandwidth is W D, indicating only one pole, dominant pole exists in its useful range. Then we said a measure of the amplifier performance is defined by what is called gain bandwidth product, which is equal to A naught into omega t. So, this is a very important parameter associated with any amplifier, the gain bandwidth product. Why? Because if I use this in a negative feedback configuration, in order to desensitize the gain with respect to the active parameter A naught and omega d, then I will let us say this is my amplifier with the gain A, and I will use it as a negative feedback. One of those configurations which we have been constantly using for demonstration of this in frequency compensation also was this R1, R2, beta let us say is R1 by R1 plus R2, that is the amount of negative feedback from output V naught. This is the amount of output fed back to the input. Then we know that the amplifier gain is going to be A divided by 1 plus A beta. This we had demonstrated earlier, or this is written as V I by beta, which is the ideal gain under the situation A goes to infinity, divided by 1 plus 1 over A beta, which is A naught to beta 1 plus S by omega d. This we had demonstrated earlier also. Okay. And we see that V naught is equal to V I by beta, okay, divided by 1 plus 1 over A naught beta, which is very small, plus S into omega d A naught beta. This can be ignored, and therefore, for the new amplifier now with negative feedback, right, the gain DC gain is 1 over beta, and bandwidth equals omega d into A naught into beta. So, this is an important aspect. The bandwidth of this amplifier after negative feedback has improved by a factor of A naught into beta. So, let us say I have designed an amplifier whose gain is sort of 10 using an amplifier whose gain was 100, let us say A naught was 100 and I am designing an amplifier with a gain of 10, that means beta is 1 over 10. So, then the bandwidth let us say is 10 to the power 6 radians per second for this. Then bandwidth for this is going to be amplifier with gain equal to 10 is going to be equal to 10 to the power 6 into A naught into beta, which is 10 times the original bandwidth. That means it will be 10 to the power 7. Gain is equal to 10. So, this is what is going to happen in widebanding. So, you can always design a wideband amplifier starting from an amplifier with limited bandwidth. You can design an amplifier with wideband and desensitized gain. Gain is going to be least sensitive to variation in A naught, wide bandwidth using this negative feedback. But we have a problem with negative feedback. As I told you, if this becomes instead of a single pole it becomes 2 pole system, then we will have an amplifier with negative feedback whose poles can become complex conjugate pair and it can start peaking. So, it starts behaving in a odd fashion at higher frequencies. This is one danger. Further, if it becomes 3 poles, we saw that there is this danger of instability occurring, it will go into oscillation. So, in order to prevent that from going into oscillation, we could take recourse to frequency compensation, making one of the poles dominant. In the process, we were cutting down the bandwidth. So, we were cutting down the bandwidth in order to make it work with negative feedback. This is where the negative feedback fails to give you the widest possible bandwidth. So, even though after cutting down the bandwidth, then gain into bandwidth is going to remain constant, and within that gain into bandwidth product you can get wideband amplifiers designed with desensitized gains, etc. But this kind of dominant pole compensation is always going to result in lower gain bandwidth product. Instead, I said we can convert that third order system into second order system by using pole 0 compensation. So, this kind of compensation we can sort of demonstrate by giving an example. So, my purpose now is to make the circuit work for the widest bandwidth possible. So, that I am designing a wideband amplifier using negative feedback. So, what kind of compensation is suited? For that particular gain that you require, you must just give enough margin so that it does not oscillate. So, this is the optimum way of providing compensation, so that it works best for the widest possible range of frequencies. So, using an example of wideband amplifier design with negative feedback, I am going to demonstrate this effect. Let us now understand this principle of widebanding in negative feedback structures by solving this example 17. An amplifier has A naught okay, of this type 200 divided by 1 plus s by 10 to the power 6 plus 1 plus s by 10 to the power 7, okay, plus 1 plus s by 5 into 10 to the power 7, this kind of pole, 3 pole. It is to be used in a negative feedback configuration, is to be used, okay, in a negative feedback configuration to give a gain of 2. That means, this is the amplifier, differential amplifier, let us say with A of this type, and it is to be used with a gain of 2, which can be done by giving a feedback factor of half, beta is equal to half. So, V naught over V I is going to be 1 over beta. So, that is actually going to be 2 divided by 1 plus something. We want to maximize this bandwidth here. Okay. What should we do? Since with this 3 pole, with 1 pole it is no problem. With 3 poles it might now go into oscillation. Let us examine. If it is not going to oscillation, please see here, if it is not going to oscillation, then the bandwidth is equal to 10 to the power 6. Actually, the gain bandwidth product is 200 into 10 to the power 6. That is the best gain bandwidth product for this already. But if it goes into oscillation, one way of compensating is to shift this down, so that these become insignificant, okay, in the frequency band. So, this is to be brought down, but that way automatically you are cutting the gain bandwidth product. So, in a wideband amplifier design, that is not done. In a general purpose amplifier, this is done so that the user can use it in any configuration he wants and see no oscillation. So, that is applicable only for low frequency purposes. The wideband amplifier, this is not done. You would like to retain this as a dominant pole, okay, which means now we have to cancel the other pole, next pole, which is influencing this in terms of phase shift, so that this becomes dominant. That means, if this is cancelled, the distance between this and this increases enormously, and another pole is going to be introduced far away, so that these 2 poles do not come into picture, and this is the dominant pole. That is the idea behind widebanding. So, let us see how practically we can do it. So, given that you can't meddle with whatever structure the amplifier has, you can only meddle with the feedback structure here. Let us see how it can be introduced in the feedback structure, so that there is a pole 0, okay, compensation for this. So, we are now discussing about how to do pole 0 compensation. I had discussed earlier itself. Now, we have to make this R and this R, but this R now can be conveniently split, let us say, to R, okay, let us say alpha R and 1 minus alpha times R. So, that the total is still equal to R, alpha R and 1 minus alpha R. So, that the total is still equal to R, such that now I can bring about a 0 here conveniently, taking portion of that R. Okay. So, I put a capacitance here. Now, for this network, let us write down how beta will look like. So, actual beta without this was half. Now, it is R divided by 1 minus alpha times R, okay, plus this resistance plus alpha R divided by 1 plus S C into alpha R. This is the attenuation beta. Okay. Now, beta has been made frequency dependent. So, it can give you the half at low frequencies as well as result in a 0 at a convenient point to cancel one of the poles and make a pole get located farther away. Okay. So, let us see whether it is done. So, here you take out this r into 1 plus SC alpha r, okay, comes to the numerator. So, you get 1 minus alpha r plus SC alpha r into 1 minus alpha times r, okay, plus alpha r. So, this alpha r plus 1 minus alpha r give you r. Okay. 1 minus alpha r plus 1 minus plus r plus 1 minus alpha r plus alpha r by 1 plus SC alpha r. So, you get here 2 r, okay, divided by this. So, this can be rewritten as, take out this 2 r. So, you get half, which is what you wanted, 2 r out. This will be 1 plus alpha SC r divided by, okay, 1 plus, okay, r has been taken out, alpha into 1 minus alpha, okay, SC r. So, as far as this is concerned, we have the 0 located omega z at 1 over alpha CR, 1 over alpha CR, and a new pole located at 1 over alpha CR, which is 0, okay, into 1 minus alpha. Look at that. That means, we have a 0 located at whatever we want, that can be located conveniently by selecting alpha CR, and then the pole is located at omega z divided by 1 minus alpha. So, by making alpha close to, let us say, alpha is, let us say, close to 1, this is actually equal to pole. Okay. The pole is going to be located farther away from the 0. Alpha, if it is close to 1, let us demonstrate this. Alpha is equal to, let us say, 1 over 19. I am just going to take it as a demonstration. Okay. Omega z is going to be 19 divided by CR, alpha equal to 1 over 19, right? Sorry, 18 over 19, okay? Alpha equal to 18 over close to 1. So, you get here this as omega z divided by 1 minus 18 over 19, which means this is equal to 19 minus 18 1. So, 19 times omega z, right. So, this is very nearly 1 over CR, right, whereas this is 19 times that omega z. Okay. So, if you select, for example, this as, let us say, 19 by 20, for example, this will be 19 by 20, which is very nearly 1 again, okay, and this will be 19 by 20, okay. So, this will be at 20 times omega z. So, just we can therefore, by selecting alpha close to 1, make the pole go farther and farther away. So, let us, for argument's sake, leave it at this, that we are going to select alpha as 19 by 20. So, that might be sufficient, let us examine. If it is not sufficient, we will select alpha further close to 1. So, alpha has been selected as 19 by 20. Then omega z is 20 by 19 times CR, which is very close to 1 by CR. That has to be made equal to, let us say, 10 to power 7. I will make this equal to 10 to power 7. So, I am now introducing in this a beta which is half, okay. Beta is going to be half. So, in my problem I will redraw this here, 200 into half, okay, this half into 1 plus, okay, S into 10 to power 7, that divided by, sorry, S by 10 to power 7, this divided by S by 10 to power 6, 1 plus S by 10 to power 7, 1 plus S by 5 into 10 to power 7, okay. And where does it introduce this pole? Is going to be at 20 times omega z. So, 1 plus S by 20 times 10 to power 7. So, is that clear? Now, this gets cancelled with this and this becomes 100. So, we saw that the A beta now gets modified as, okay, 100, same as value as before, this remains the same. Now, the second pole has got shifted from 10 to power 7 to 5 into 10 to power 7, and a third pole has been introduced at S by 20 into 10 to power 7. So, this is the new modified A B, where this one, yeah, this is 10 to power 6, thank you. So, first pole remains at 10 to power 6, second pole has got shifted from 10 to power 7 to 5 into 10 to power 7, and the third pole is 20 into 10 to power 7. This has been reintroduced. Now, let us see whether this is satisfying the criteria for stability. What does it mean? This magnitude of A beta should be less than 1 when the phase of A beta is 180 degree. When will the phase become 180 degree? At a frequency omega approximately equal to 5 into 10 to power 7, 20 into 10 to power 7 under the root. It is going to be product of these two frequencies under the root, which is nothing but 10 into 10 to power 7 roughly, right. So, at this frequency there is going to be phase shift becoming equal to 180 degree now, right. So, what happens? It is 100 divided by, okay, 1 plus, now 1 plus S by 10 to power 6, at this frequency this 1 can be ignored. So, magnitude of this becomes simply, right, 10 to power 8 divided by 10 to power 6. So, this itself brings in an attenuation of, okay, 100 here. Right. Other things now, 1 plus, okay, S is again 10 into 10 to power 7. So, there is a factor of 2 here. So, 2 squared to the power half, 1 plus omega by this squared to the power half, that is the magnitude of this. Okay. Then other one is 1 plus half squared, okay, to the power half. Square root. So, this is the magnitude, and obviously this is less than 1. We do not have to even calculate, because this is 100 by 100 and these factors are greater than 1. So, this is less than 1 and therefore, is less than 1 and therefore stable. Earlier we saw that this was greater than 1, okay, and it was therefore unstable, and now it is less than 1 and it is therefore perfectly stable, and therefore there is no problem. We can build this, and it has gain bandwidth product which is the same as the original amplifier which we started with, that is 200 into 10 to power 6. That is the gain bandwidth product. That means with a gain of 2, I can use it up to 100 into 10 to power 6. With a gain of 2, okay, bandwidth is going to be 100 into 10 to power 6. So that the gain bandwidth product remains the same. So this is the best design possible. For the widest possible frequency range, you can use it as an amplifier with gain of 2. Okay. Now, the question in the previous problem arose as to whether this is unstable for the design given for a beta equal to half. Only when this is unstable for a beta equal to half, as it is, right, that the modification that we have suggested comes into picture. Suppose this is not unstable, then the gain bandwidth product is straight away available as 200 into 10 to power 6. You do not have to do any frequency compensation. Therefore, let us verify. I had actually given you a problem where A has been so chosen that just as such, if you use, it is unstable. Let us make sure that it is unstable. Then only the pole 0 compensation becomes necessary. So, now A beta is going to be 100 divided by 1 plus s to power s by 10 to power 6, 1 plus s by 10 to power 7, 1 plus s by 5 into 10 to power 7. By cancelling this out and making this become a second pole and introducing a pole far away, we were able to make it stable. But if this itself is stable, there is no need to do this pole 0 compensation at all. Let us see. Now, the frequency at which the phase shift of this becomes equal to 180 degrees is roughly equal to 10 to power 7, 5 into 10 to power 7 under the root, which is root 5 into 10 to power 7. Now, magnitude of A beta at that frequency equals 100, that is 200 into half, that is what has become 100 there. Okay. So, that divided by, now this is dominant, okay, because it is root 5. So, that 1 can be ignored, root 5 into 10 to power 7 by 10 to power 6. This is the attenuation caused by this pole, that this is still dominant. At the other pole, this thing is 1 plus, okay, root 5 into 10 to power 7 by 10 to power 7, root 5 squared. So, 5 to the power half, that is the magnitude of that. And then the magnitude of this is 1 plus 1 over 5, okay, to the power half. So, you can see that this is greater than 1. This is 100, this is root 5 into 10, which is not much, this is root 6, this is almost nearly 1. Okay. So, this is root 30 into 10. Okay. So, how much is it? root 30? So, this is 54.7 and this is just root of 1.2 about, okay. How much this whole thing is? So, you can
1.669.
So, the whole thing is 1.67. So, greater than 1 and therefore, it obviously needs the kind of frequency compensation, pole 0 compensation that we have introduced, that can be easily introduced in order to retain the gain bandwidth product at 200 into 10 to power 6. So, this kind of wideband amplifier design is commonly adopted when the system is pretty complex, right. There are 3 or more poles associated with it. If it is less than 3, if it is 2 or 1, there is absolutely no frequency compensation and the gain bandwidth product is straight away the gain into the first pole frequency. Okay. Let us now discuss something about negative feedback and wideband amplifiers and non-negative feedback structures for wideband amplifiers. If I am trying to make the gain insensitive to active parameters, the best way is to give overall feedback. With cascaded stages. That is, you cascade a number of stages so that the loop gain becomes very high, DC loop gain becomes very high and then give overall feedback, then it desensitizes the gain. Okay, after feedback. This is the best way to work with overall feedback, but overall feedback always results in multiple poles. Results in multiple poles. For example, each stage will have input time constant that is input capacitor into input resistor, okay, and output time constant. This is input capacitance into input resistance, output capacitance into output resistance. So, both of which will introduce a pole each, and omega p2 is going to be in whatever transfer function that you are going to obtain from that stage. Okay. Primarily it will introduce an input time constant and an output time constant and introduce 2 poles. So, each stage will introduce 2 poles. If there are 2 stages, there will be minimum of 3 poles: input, intermediate and output. If there are 3 stages, there will be 4 poles. There is 1 stage, there is likely to be 2 poles. So, n stages will have at least n plus 1 poles, at least, Other frequency dependent factors may increase the number of poles. The minimum number of poles, okay, first one stage will be 2 poles, 2 stages will have 3 poles, 3 stages will have 4 poles, n stages will have n plus 1 poles. And therefore, we have already seen that we will get into problem most probably when we connect 2 stages, because it will result in 3 poles, and most probably, right, the frequency compensation may become necessary here, cutting down on the bandwidth maybe, right, if the loop gain is high. So, definitely in 3 stages, right. So, normally overall feedback is not given because of possibility of instability that will arise frequency above 2 stages, very rare. So, you will use most of the time for wideband amplifiers only one stage, okay, which is pretty safe. A single stage is pretty safe for negative feedback. So, only local feedback is preferred. Local feedback will necessarily have less loop gain and will be more sensitive to active parameters than overall feedback, but the advantage is that there is no need for frequency compensation. So, it can be a wideband configuration. So, single stage structures are normally preferred, okay, for wideband application rather than multiple stages with overall feedback. Multiple stages with local feedback therefore are suited for wideband application. So, we will therefore now discuss about how to design wideband amplifiers, simple amplifiers, and cascade them together to get very wide bandwidth. So, please remember that more than 2 stages overall feedback is never adopted because it results in problem of oscillation or instability invariably, and local feedback is resorted. That means, single stage will always have negative feedback in order to improve its bandwidth of performance. When you cascade wideband amplifiers, again remember that you can prove that overall bandwidth gets reduced. If they are having the same bandwidth and I cascade all the amplifiers together, we had earlier also shown that the overall bandwidth gets reduced because of cascading. So, if you want a certain bandwidth for the cascaded structure, you have to allocate for individual stages wider bandwidth than what you ultimately want to have. So, this kind of design is invariably needed in design of wideband amplifiers. Okay. So, let us now consider single stage structures and how to improve bandwidth of single stage amplifiers. So, consider for example, the common emitter amplifier. When I discuss common emitter amplifier, that discussion is equally well applicable to differential amplifier, because a differential amplifier for differential signal can be converted into 2 common emitter amplifiers. Okay. So, if you have a common emitter amplifier feeding on to some load here, because of capacitors, there will be input capacitor. In a transistor, this will be the stray capacitor plus the input capacitor of the transistor, which is normally called CB dash E, right, and then there will be capacitor between the base and the collector, which is called CB dash C. And there might be some output capacitor here, okay, which we will call as CC collector. So, what happens in this case is that I can convert this configuration into approximately a configuration with 2 time constants by saying that this particular amplifier has a gain from here. If this is V I, okay, this output voltage is going to be minus G M R C into V I. This we have done earlier. G M is equal to 1 over R E, small r e. R E is equal to V T by I E Q. So, this capacitor now appears at the input as a larger capacitor. So, I can convert this capacitor, this is C B dash E, this C B dash E is connecting input to output. So, if this is V I and this is G M times minus G M times R C times V I, then the current in this is V I plus G M R C V I into S C B dash C, that is admittance. That is the current in the circuit. So, as far as V I is concerned, it is going to appear as this is going to be the current that is going to be done. So, V I by I I is going to be 1 over S C B dash C to 1 plus G M into R C. So, effectively you get a capacitance which is C B dash C into 1 plus G M into R C. This is an important phenomena. This is called Miller effect. This capacitor is called Miller capacitor and this is called Miller effect. Any amplifier which has a capacitance between its input and output, that capacitance gets amplified by a factor of 1 plus gain, that is the Miller effect. So, effectively the input capacitor C I is going to be C B dash E input capacitor plus C B dash C into 1 plus G M into R C. And as far as the output is concerned, output is G M R C times higher than the input. So, this capacitor is going to be appearing as C B dash C plus 1 by G M R C. So, that is very high. So, it is essentially going to appear as C B dash C. So, output capacitor is going to be C C plus C B dash C approximately. Whereas, the input capacitor, because the input is going to be amplified here as minus G M times R C, the current is going to be more. Okay. So, output capacitor is essentially C naught equal to C C plus C B dash C, input capacitor is C B dash C plus C B dash C plus. So, we have now a means, whether it is a field effect transistor or bipolar transistor, same thing is applicable, right. Those capacitors are the culprits in bringing down the bandwidth. So, essentially as far as this common emitter amplifier is concerned, omega P1 is going to be the pole. If you consider this R I C I, what is R I? That we know, that is a common emitter amplifier, R E into 1 plus beta, that is the input resistance. Okay. That into C I, which is C B dash E plus C B dash C plus 1 plus G M, that is R C divided by R E. Okay. So, this is the pole of the common emitter amplifier. Because of Miller effect, this capacitance is boosted up. the output time constant omega p2 1 over R naught C naught, which is roughly 1 by output impedance of the structure. If it is very high, it is essentially R C, okay, into C naught, which is C C plus C B dash C. You can see therefore, that if R C is of the same order as R E into beta plus 1, normally omega p 1 becomes the dominant pole, because this capacitor is going to be very huge compared to this capacitor. So, it is normally the input time constant which fixes up the dominant pole in a common emitter amplifier. So, whether it is a common emitter amplifier or common source amplifier, okay, the same thing is applicable. So, you can therefore see here that the bandwidth of the common emitter amplifier is nothing but omega p 1 in most of the cases. Bandwidth of the common emitter amplifier is omega p 1. R E is V T divided by I E Q, this we know. Now, bandwidth of common emitter amplifier is this. How to improve this bandwidth further? This is our purpose of discussion in this wideband amplifier category. Obviously, I cannot do anything about this. I have to somehow reduce the effect of the capacitor. For that purpose, what I do is, this common emitter amplifier, let it have low voltage gain. So, what do? I will now feed this into another common base structure. This is a common base structure. So, this current is going to be going into the common base structure input current. So, output current is same as this. So, there is no difference as far as low frequency picture is concerned, because this current is going to be same as this current, and I can put R C here, because the common base has a current gain of 1. So, as far as I am concerned, nothing has happened for the low frequency performance. Right. This particular current is now going into flow into this R E, and is going to appear as alpha times that current. So, and now it is flowing through R C. Earlier it was going into R C. So, as far as this structure is concerned, the gain still remains as G M into R C minus G M into R C, because even the phase has not changed. So, this configuration of cascading common emitter with common base is called a special structure called cascode, which is one of the most popular wideband structures. Why wideband? How did it get wideband? Okay. This wideband comes because of gross impedance mismatch here. This earlier was directly going into R C, which was maybe very high, but now it is going into small R E. So, what will be the gain of this now? This Miller effect is reduced, because this R C is gone here. As far as this stage is concerned, R C is not there. Okay. So, this is R E itself, if they are operating at the same current. So, earlier R C over R E was very high, now it becomes R E over R E. So, it becomes simply 2 times C B dash C. So, bandwidth now of cascode simply goes up. Maybe this particular thing is still dominant, we do not know, because this capacitor may be still fairly high compared to C B dash C, okay. But the bandwidth here has improved enormously. As far as the low frequency gain is concerned, it still remains G M into R C. So, I can now write down the complete expression for the gain omega p1 and omega p2, okay, being these two for the cascade structure. Okay. The low frequency gain remains the same. Earlier of course, it was being replaced by 1 plus GM into RC. That is the expression for the gain, complete expression for the gain. So, bandwidth is still equal to omega p1, it has improved drastically. So, this is a wideband, okay, amplifier, a cascade structure which is nothing but a common base cascaded to common emitter cascaded to common base.